Okay, so now we have tokens and sentences. And it already looked like a lot of work, right? Just to get here. But we haven't really done any real natural language processing yet. So let's talk about another step that's often done, which is a morphological analysis of the document. So in most languages, words are changing, and they are changed through a morphological process that's called inflection. So words change based on case, gender, number, tense, and so on. For example, the word car changes to the plural from cars, or the verb give changes depending on the tense to gives, gave, given. So the goal in morphological analysis is to somehow normalize these words, to be able to go back from one of these variants to the original so-called root form of the word. And there are two approaches for doing this, and they are called stemming and lemmatization. In stemming, what you do is you take one of these variants and you reduce it to a base form. And in lemmatization, you reduce the words to their lemma. What's the difference? So the lemma is the original version of the word. For example, for one of these here, the root form, the lemma is give. For cars, it is car. In stemming, you just reduce the word to any kind of base form. I'll show you an example in a minute, but it doesn't have to be a real word. It's just a base form of the word. So stemming is something that's typically used in information retrieval. When you build something like TF-IDF vectors, you don't want to have all of these additional dimensions just for these different variants. So one thing you do is you run the words through a stemming pipeline first, and then the resulting vocabulary is what goes into your TF-IDF vectors. How you do the stemming depends again on the language. In English, there is a standard algorithm, the so-called Porter stemmer, which is implemented in many libraries. That can be done very easily, very fast. But the main problem is that it's basically a kind of suffix stripping. So for words like computers, computing, it's just removing the suffix. And the stem it generates, comput, is not actually an English word. So this is what's meant with what I said here. We're reducing it to a base form, but this base form doesn't have to be a real word in the language. So this works actually quite well for things like TF-IDF vectors. We are not really interested in all of these variants. And because it's just one dimension in the vector, it doesn't matter that it's not a real word in the language. But the downside is that it makes a number of simplifications that are really not helpful when you want to do a deeper analysis. For things like army and an arm, again, it strips the suffix and both are reduced to the word arm. But there's a big difference between an arm and an army. Likewise, for stockings and stocks, it both reduces them to stock. So you can see if you're interested in a deeper semantic analysis, the stemming isn't helpful. So stemming is easy, fast. There are lots of language files available for standard libraries like Lucene. You can just load the corresponding rule file for the language and you make these stems. They work well for things like TF-IDF vectors, but they are not so good for deeper semantic analysis. So this is where you do lemmatization. Lemmatization means you want to find the root form, the so-called lemma of the word, which has to be an actual word in the language. So there are a lot less errors that you produce than in stemming. But this requires a deeper analysis because you have to simulate the morphological process that changed the word in the beginning. So it's a lot more complex, it's slower to run, and again, it's language dependent. But for many of the things that we do, more detailed semantic analysis, you need this additional information that you get from lemmatization. Later, you'll see where these lemmas appear in spacey processing. So let's come to the next step, which I showed you in the introduction already on the part of speech tagging. So the next step is to find out what each of these tokens, what the category of each of these tokens is. And the standard processing that you do is this part of speech tagging, where you assign a tag to every word in the sentence. And you can see that these tags have a number of abbreviations. I'll talk about these in a second. So like I said earlier, this is something that can be done reliably using a probabilistic analysis. Don't get confused, this is not yet parsing. We're not building something like a parse tree. This is something that comes later based on the output of part of speech tagging. So where do these funny abbreviations come from? They come from a so-called tag set. So the tag set defines how many different tags you use for processing a document. So typically for a language like English, they fall into these main classes: nouns, adjectives, verbs, adverbs, pronouns, determiners, prepositions. And then in there you have additional subclasses, like proper nouns, singular nouns, and so on. So the number of different tags that are being used, these abbreviations here, they differ depending on the tag set. And in practice, some tag sets have, for English, 45 different tags to more than 146 tags in the C7 tag set. You can imagine the more fine-grained it is, the more information you have for later processing, but also the more difficult it is to get a high accuracy. So this tagging is basically a machine learning approach. You need to have a corpus where each token is manually annotated with the correct tag. Then you learn the probability distribution. You store them in a model. Then you load that model later on and you can run it on a new document. So in general, this works very reliably, around 96%, if you stay in the same domain, meaning if you trained your part of speech tagger on news documents and then you run it again on news documents. If you train it in one domain, like news documents, and then run it on a different domain, like medical documents, obviously the performance is going to be a lot worse. So there are lots of different algorithms that are being used, decision trees, support vector machine, hidden Markov models, and so on. Again, if you take a natural language course, you're going to look into a lot more detail on how to learn these tags, how these different algorithms work for computing the tags. Here, we're just going to use one of the pre-trained models that come with a library like spaCy. So how do you work with it in spaCy? Well, like before, you load the language model, which gives you the pipeline. The pipeline for English already has a part of speech tagger in there, so we can run it on a document. Like here, Apple is looking at buying UK startup for 1 billion. And then earlier I showed you, now in this document, you have tokens. We again print out all of the tokens, but now we print out not just the text, we print out the lemma, the part of speech tag, and a couple of other information. So lemma, I explained earlier. So you can see here for the word looking, it found out that the lemma, the base form is look. For buying, it is buy, and so on. And you see the different part of speech tags it designed. For example, startup is a noun, Apple is a proper noun, and so on. So once you worked with this, you get the feeling for these different tags and you sort of memorize them. In the beginning, you probably have to look them up. If you don't know what an NNP is or an ADJ is, you have to find out either by looking at an online reference, or you can use the built-in explanation method from Spacy. So you can just say spacy.explain NNP, and it will tell you this is a proper singular noun. The concrete tag set that's being used by the default part of speech tagger is using the universal dependency scheme, and the documentation you can find on the link here. So again, try it out using the next task on the worksheet, and I'll see you back afterwards.